Hello everyone, welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In my previous lecture, we have discussed about NLP, Natural Language Processing, and the various NLP tasks. In today's discussion, we will speak about text preprocessing and text representations. So the contents for today's lecture goes like Introduction to Text Preprocessing, techniques of text preprocessing like tokenization, stop word removal, stemming and lemmatization, parts of speech tagging. In text representation, we will speak about hot encoding, bag of words, and TF-IDF, which is term frequency, inverse document frequency. So let us start with an introduction to text preprocessing. What is text preprocessing? Text preprocessing is an essential step in natural language processing that involves cleaning and transforming unstructured text data to prepare it for analysis. So as I was telling that you give some input text, and when it is passed through the model, we expect the model to use NLP technique and give some output in the form of text. Okay. Now when we are giving an input as a text, the machine cannot understand text. Okay. So it has to be changed, it has to be pre-processed in such a way that the machine understands what the text is conveying, what is the information that is present in that text. Based on that one, the model will give the output. Okay. So text pre-processing is a step that involves cleaning and transforming the unstructured text data to prepare it for analysis. Now, there is a word unstructured text data. What exactly is the meaning of that one? Unstructured text data means they are free form and human generated. It can vary in length, style, grammar, vocabulary, and it is often noisy. Noisy means it can have typos, it can have emojis, it can have abbreviations. So all these things are coming in the form of a text. Okay. So they are, as they are human generated, they are of any, any sentence can be, a sentence can be of any length depending on how the user wants to convey the message. The grammar may be different, the vocabulary used may be different. So all these things makes it the text as a unstructured data. Okay. So this unstructured data requires cleaning and transformation so that it can be processed to a state where the machine will understand. Now, various techniques of text preprocessing are tokenization, stop word removal, stemming and lemmatization, parts of speech tagging. So, these are the 4 techniques that we will be speaking about today. Okay. Now, text processing in NLP, we will start with tokenization. Tokenization is a fundamental process in NLP that involves breaking down a stream of text into smaller units called tokens. That means if we have a big sentence, we will divide it into small chunks, and those chunks will be called as tokens. Now there are various kind of tokenizations. One is sentence tokenization. We will see an example. Say we have 2 sentences like I like mangoes and they are sweet. Okay, I like mangoes, they are sweet. So these are the first and the second line of a paragraph. Now if I do a sentence tokenization, we get the tokens like I like mangoes, that is one token, and they are sweet, that is another token. Okay, so this is called as sentence tokenization, which basically means dividing your entire paragraph into different sentences, and these sentences are called as tokens. Word tokenization. So I like mangoes. If I do a word tokenization, I get the separate words as separate chunks or tokens. So word tokens here will be I is one token, like is another token, mangoes is another token. Okay. So like this, these are called as word tokenization. Subword tokenization. What is that? I like mangoes. So if I do a subword, that means breaking a word, okay, into 2 chunks. So I will remain as I, that's a separate token. Like will remain as like as a separate token, word token. Mangoes, mang, and then goes. Okay. So these are 2 separate tokens, mang, goes. Okay. So That is called as subword tokenization. And then we can have character tokenization, where we will have all the characters as separate tokens. Like I like mangoes, so I becomes one separate token. Then there is a space that becomes another token. Then like L becomes one token, character token, I becomes one more character token, K becomes another character token, E becomes another character token, and so on. Okay, so this is called as character tokenization. So tokenization is a process where you are breaking down a stream of text into either sentences, words, subwords, or into characters. Then we have something called as the stop word removal. So stop word removal, these are the most common words in any language, like articles, prepositions, pronouns, conjunctions, etc. Okay, and if you see, they do not add any information to the text. Removing them improves computational efficiency. So, they do not add any information. A, the, and these things do not add information, but if they are removed from the sentence, what happens is we don't lose any information. At the same time, it improves the load on the computer, the load on the machine in terms of computational power requirement and memory requirement. Okay. Removal of such words does not show any negative consequences on the model we trained for a task. Okay. Like I never tasted a pizza like that before. Okay. So this is a sentence. We do a word tokenization where we get I have never tasted a pizza like that before. So these are all separate word tokens. Now we are identifying what are the stop words, and we see I, have, like, that, before. So these are all the stop words, and if you see, if I take out those stop words, I'll get never tasted pizza. So this is the the gist of the information that is put in the sentence. I have never tasted a pizza like this before. That means I have never tasted a pizza. Okay. So now I have never tasted a pizza like this. So never tasted a pizza is the important information that you are getting from this sentence. Okay. Then stemming and lemmatization. What is stemming and what is lemmatization? We will see. Stemming is a technique where words are reduced to their base or root form by removing the suffixes or prefixes. Whereas lemmatization is a sophisticated technique that transforms words to their base forms known as lemmas, considering the word's meaning and context. Okay. So, we will see both of them are actually transforming the word to something related to the base form. Okay. Now, there is a subtle difference between stemming and lemmatization. We will see here. Suppose we have the word changing, change, changed, changer. Okay. So, if we see, all of them is having ching. So, this is the process, this is the process of stemming, where changing becomes chang, change becomes chang, that e is removed because it is treated as a suffix. changed, changed becomes once again chang, and changer also becomes chang. Now, if you see, there is no dictionary word which is having this chang. Okay. So, but stemming have transformed the words changing, change, changed, changer to some word which is chang. Okay. So, this is stemming. Whereas in lemmatization, what happens is, it takes the same words changing, change, changed, changer, and then it changes into the base word which is change, that is change. Okay. And if you see here, this change is a dictionary word. It has a meaning, whereas this chang, it is not a dictionary word. It doesn't have a linguistic knowledge. So, in stemming, this is an example of stemming. where it doesn't have a linguistic knowledge, it is just removing the suffix and prefix of the text and then making it like a base or root form. Whereas in lemmatization, what happens is they change into they transform the text into something which is present in a dictionary. That means it has a meaning of its own. So this is stemming and lemmatization. Why we require it? Because once we understand, there can be various forms of a word like changing, change, changed, changer. But once we understand what is the root word for all these forms, we will be able to understand the meaning that is conveyed by this text. So that is the reason stemming and lemmatization becomes a very important part of your text preprocessing. Then we will go into something called as parts of speech tagging. What is this parts of speech tagging? From the name itself, we can tell that there will be a text and then each word of the text or the sentence will be tagged with some parts of speech. We know parts of speech are, in grammar, we have this noun, verb, adjective, adverb, pronouns. So all these things. So every word in a sentence will be tagged with something with some parts of speech. So we will have an example. So parts of speech tagging involves assigning a grammatical category such as noun, verb, adjective, etc. to each word in a sentence. Helps machine understand the syntactic structure of the sentence, which is crucial for different tasks. We will come into the tasks. Now, before going into the task, we will try to understand what is this syntactic structure means. This is a word which we will be using, in our further lectures as well. Syntactic structure, what exactly syntactic means? Syntactic means it is related to the grammar and structure and the rule for arranging words or symbols in a sentence. So basically it captures the grammar of a sentence, okay, and helps if the syntactic structure of a sentence is understood by the machine, that knowledge is used or which is crucial for tasks like machine translation, information extraction, question answering, text to speech conversions, etc. Okay. So, this grammatical context or the grammatical knowledge of the sentence is needed by the machine to understand, because that will help in the further processing and doing the tasks, completing the tasks like machine translation, information extraction, question answering, text to speech conversion and other NLP tasks. So this is called as parts of speech tagging and why it is required. Now we will just have a look into an example. A quick brown fox jumps over a lazy dog. So a is an article, so it is tagged as a determiner. So and it is given by DT. Then quick is an adjective, it is given by JJ, and then brown also is an adjective, and then fox is a noun which is represented as NN, and then jumps is a verb, so it is tagging jumps as a verb. Then over is a preposition and it is represented by IN in parts of speech tagging. A is once again an article, it is a determiner, and then lazy is an adjective, so it is JJ here, and dog is a noun, so NN. So this is an example of a sentence where each and every word of the sentence have been tagged with the parts of speech. Then we come to something called as the text representation in NLP. So we have till now we have seen what are the various kind of text pre-processing, and as I told in the beginning itself, this text pre-processing is required for the machine to understand what meaning is conveyed by the sentence. So that is done by the text pre-processing. Now text representations in NLP. We will look into what exactly text representations mean and how they are achieved. Okay. Suppose we have some documents, and these documents, we have multiple documents, and we want these documents to be read by the machine and generate some output. Okay. So these documents, the input to the documents needs to be changed into some mathematical form which is usually a vector form. Okay. So, the text that is present in the document will be represented in the form of a vector, and these mathematical representations only will be understood by the machine or the model, because the model will not understand the text, the semantic or the meaning that the text or the sentence is conveying, that the machine will not be able to understand if the input is in the form of text. So, what happens here is that text, whatever words, whatever sentences, whatever paragraphs we are giving as input to the model, it is first changed into some vector, a mathematical form, and then it goes to the neural network, and then we expect an output from there. Okay. So, this is called as the vector is called as the text representation in in any mathematical form, and this is very much required because machines will understand only math in the form of vectors. Okay, in any mathematical form, if we give the input, our machine will be able to handle that one. Okay. Now, text representations involve converting raw text data into machine readable form. Okay. And there are two types of text representations which are widely used, and these are discrete text representations and distributed text representations. So, today in this lecture we will look into the discrete text representation. Okay. We will look into what are the different kind of discrete text representation that we use in NLP. So, discrete text representation. So, we will just give a definition. What is text representation? It is a technique used in NLP to transform raw text into numerical features that capture information needed for computational processing and learning. Okay. Now, there are various techniques of discrete text representation: one-hot encoding, bag of words, term frequency inverse document frequency, which we call as TF-IDF. This is also a technique of discrete text representation, and then we have n-grams. Okay. So, these are the various forms of discrete text representation. In our today's lecture, we will see one-hot encoding, bag of words, and TF-IDF. The n-grams we will take up in my next session. Now, I will introduce you all with some key terminologies that are related to text representation, because we will be using these terminologies quite often when we are going forward. Corpus. What is corpus? All text data or records of the dataset together is known as corpus. So, you have say multiple dictionaries, multiple documents, multiple online resources, everything put together is your corpus. Okay. Vocabulary. What is the meaning of the term vocabulary? All the unique words present in the corpus. So, that constitutes your vocabulary. All unique words, whatever unique words are there in the corpus, all of them make your vocabulary. Document. One single text record of the dataset is a document. One single text record, one single record is a document. Word. The words present in the vocabulary, they are termed as words, normal words in text representation. Now, we will look into what is this one-hot encoding. One-hot encoding is a method for converting categorical variables into binary format. So, we all know categorical variables, they represent qualities or characteristics like color. So, when we have colors like red, green, blue, orange, something like that, we have to change it into some binary format for processing it further. Now, it changes every word, one-hot encoding changes every word to a v-dimensional vector. Now, we will have a look into what is exactly this is. Suppose we have categorical variables of some color names red, blue and green, and this is the vectors. Red is given 1 for the first this row, and blue and green are 0. For the second color blue here, this corresponds to blue here, and red and green are 0 here. For the third row here, where we have the color green, we have for green 1 and red and blue are 0. So, if we see, each color is now represented by a vector. The red color is represented by the vector 1 0 0, blue color is represented by 0 1 0, green is represented by 0 0 1. So, these are your one hot encoded vectors for the color red, blue and green. Now, why one hot encoding is required? I can always, can I name them as red equal to 1, blue equal to 2, green equal to 3? Can I do it? If I do it, is there any problem? If there is a problem, what is the problem? We'll try to see that one. Now, suppose we use numbers like red equal to 1, blue equal to 2 and green equal to 3. The model might think that your green, which is having number 3, is greater than blue and blue is greater than red. That means it is giving some more weightage to green because that number is higher, then blue and then red, which isn't true. Okay. So, one hot encoding, it eliminates this ordinality. Okay. That is very important, and if we cannot give numbers to these categorical variables, we need to represent them in the form of some vectors, and that is what our one hot encoding does. Then we will look into what are the limitations of one hot encoding. Are there any limitations? Yes, it's a large dimensional sparse vector representation. Means if we have a big sentence and we want the representation of one particular word in that sentence, then all the words in that sentence will be 0, only that word will be 1. So, it's a sparse vector representation. For an example, we will see the quick brown fox jumps over a lazy dog. Okay. So, the vector representation of fox, see, for quick it is 0, for the it is 0, quick it is 0, brown it is 0, for fox it is 1, correct, jumps it is 0, over 0, 0, lazy 0, dog 0. That means we are having a large dimensional vector, but only this one is having the information encoded. That is, it is a large dimensional sparse vector representation, which is computationally expensive. Also, it treats each word as independent of the other, even if both the words are together. Like, we will just take an example. Suppose we have the word notebook. So, the vector representation of one hot encoding is notebook is given by the vector representation of note plus vector representation of book, even though these are two, notebook is a single word. So, these are the limitations of one hot encoding. Next, we move to another text representation, which is called the bag of words. What is bag of words? The bag of words model is a way to represent text data numerically so that the algorithms can process it. Once again, it is in the form of numbers we are representing the text. Treats each document, sentence, paragraph, etc. as a bag of words. So, you have a document. So, that document contains say 100 words or 200 words. That collection of words is called as the bag of words. So, each document is treated as a separate bag of words. Okay. It ignores the grammar and word order, but if the word order is ignored, the meaning is not conveyed properly, that we will see later. So, it does not take the grammar and word order into consideration. Only cares about the frequency or the presence of word. It cares about two things. One is the frequency at which the words are getting used in that sentence or paragraph, or the presence or absence of that word. Okay. So, we will have a look into some examples of bag of words. So, we have two sentences. I love NLP, that is my sentence 1, and I love deep learning, which is my sentence 2. Okay. Now, my vocabulary, which is a collection of the unique words in my sentence 1 and sentence 2, consists of I love NLP and then deep learning. So, these 5 words constitute my vocabulary. Okay. So, if I put it in a this tabular form, so in a one hot encoded kind of a structure, this I love NLP deep learning. So, in sentence 1, I is there 1, love is there 1, NLP is there 1, then deep is 0, learning also is 0, because deep learning is not there in the first sentence. Whereas in the second sentence, I love deep learning. So, these 4 are there, NLP is not there. Okay. So, if we make this kind of a table, then the vectors, we can get the vectors from this kind of representation, and the vectors for sentence 1 and 2 are like, for sentence 1 it is 11100, which is shown here, and for sentence 2 it is 11011, which is your vector representation for sentence 2. Okay. So, this is bag of words technique. We are representing it in the form of numerical values, taking the vocabulary and the number of times or where all these are used, taking them into your vector. Okay. Now, limitation of bag of words. Suppose I have two sentences. Okay, cat eats fish and fish eats cat. These are two sentences. Okay. Now, my vocabulary will be cat eats fish. Okay, cat eats fish. Fish is still here. Eats also we have already taken. Cat also we have taken. So, the vocabulary only is cat eats fish. Now, if you see here, sentence 1, cat eats fish, both are 111. Sentence 2 also, cat eats fish, 111. Now, both sentence 1 and sentence 2 are having the, according to bag of words, the vector representation is 111, 111. But does sentence 1 and sentence 2 have the same meaning? No, it doesn't have. Here, what is happening is bag of words is not taking into consideration the order at which the words are placed, which is very important to have a meaningful message. You know, if you want a meaningful message to be conveyed, your order of words is very, very important. Okay. So, word order information is lost in bag of words. Okay. So, this is a limitation of bag of words. Then we come to something called as the term frequency, inverse document frequency. Now, from the term itself, we can see it is related to the frequency or the number of times a word is getting used somewhere. So, we will look into, there are two terms, one is term frequency and there is another term called as a inverse document frequency. We will look into what are they and how they help in text representations. We call it as TF-IDF, term frequency inverse document frequency, is a statistical measure used to evaluate the importance of a word in a document within a collection or corpus of documents. More the number of times a word is used in a document or in a corpus, more important the word is. Okay? So, that is the main notion. It combines two key factors, term frequency and inverse document frequency. Okay. So, we will see what is this term frequency. Term frequency is defined as number of times the term T appears in the document D. So, term frequency within bracket T comma D means number of times the term T appears in the document D divided by the total number of terms in document D. Okay. So, that is the definition of term frequency. Then we have the inverse document frequency or the IDF within brackets small t and capital D. It is equal to log of total number of documents in the corpus D, total number of documents in a corpus if it is D, capital D, that divided by the number of documents containing the term small t, log of that one gives me the inverse document frequency. Okay. So, these are the two definitions of term frequency and inverse document frequency. Now, we will see how to calculate that one. Suppose we have two documents. Document 1 has the cat sat on the mat. Document 2 has the dog played in the park. We have 3 documents. Okay. And document 3 has cats and dogs are great pets. So, total number of documents in the corpus is equal to 3. Okay. So, capital D equal to 3. Now, calculation of term frequency score for the word cat. How do I do the term frequency score for the word cat? So, we know term frequency is equal to number of times T appears in document D divided by the total number of terms in document D. Okay. So, if we see document 1, the cat sat on the mat. Number of times the cat appears is 1. Total number of terms, the cat sat on the mat. 1, 2, 3, 4, 5, 6, 6. So, TF score is 1 by 6. In document 2, we are calculating TF for that word cat. So, in document 2, the dogs played in the park. So, there is no cat. So, number of times cat appeared is 0. Total number of terms is 1, 2, 3, 4, 5, 6, once again 6. So, TF score is 0 by 6. In document 3, cats and dogs are great pets. So, number of times the cat appears is 1. 1, 2, 3, 4, 5, 6. Here also total number of terms is 6. So, it is 1 by 6 is the TF score. Okay. So, this is the way term frequency for a particular word is calculated. Then we will see calculation of IDF score for the word cat. How do I find out the inverse document frequency for the same word cat? So, here is the equation IDF equal to for the cat T in the corpus which are having D documents equal to log total number of documents in corpus D divided by the total number of documents containing contained in number of documents containing term T. Okay. So, now total number of documents in the corpus D, that is 3. Okay. Total number of documents in the corpus. So, capital D is 3. Number of documents containing the term cat 2, because we have seen document 1 and document 3. In my previous slide, we have seen these are the 2 documents in which we have the term cat. Document 2 was not having that one. So, number of documents containing the term cat is 2. Now, IDF for cat in this D number of documents is equal to log of total number of documents in the corpus D, which is 3, and number of documents containing the term T is 2, which is log of 3 by 2. Okay. So, this is the way we do the IDF calculation. Then TF-IDF calculation is done by multiplying the term frequency with the inverse document frequency. So, for document 1, TF-IDF for cat document 1 and your corpus is having 3 documents is a multiplication of these 2, which we have done the multiplications. You can cross check that one. For document 2, it is the word is cat document for document 2 and the number of documents in the corpus is capital D is 0, because 0 we got from our TF, because our document 2 was not having the word cat into 0.716, which is from here, which is equal to 0, and similarly for document 3 also we can do the calculation. So, this is the way we do the TF-IDF calculation or score calculation for any term in a corpus. Okay. So, and it is completely a frequency based technique, it is a statistical technique, and with this information, the more the number of frequency or the more the frequency of usage of a word in a text is seen, that means that word is having much more importance in that context. Okay. So, with this one I come to the end of today's discussion. In my next session I will start with n-grams, which is also a continuation of this discrete text representations. So, before I conclude the session, let me summarize quickly what all we have gone through, what all we have learnt in today's discussion. So, we have seen what are the text pre-processing techniques, why they are required. They are required because we need the machine to understand human language, and for that one we need to do a lot of text pre-processing, that is dividing a sentence into small tokens, or dividing a paragraph into sentence tokens, word tokens, subword tokens, and making it small in small chunks. And then what we do is we remove all the unwanted information that is present, like stop word removal, and unwanted information means which do not give extra information about the context, only the, like, these are the things which we tend to remove from the sentences in stop word removal. Then we do text processing like stemming and lemmatization, which changes any form of a word into their root words with some meaning in case of lemmatization. And then after stemming and lemmatization, we have seen the parts of speech tagging. This parts of speech tagging is required for understanding the syntactic structure of the sentence. Once we can tag each and every word of a sentence with a parts of speech, the entire grammatical context of the word of the sentence or the paragraph of the sentence is captured, and that helps in further processing like machine translation, text summarizations, and various NLP tasks. Then we have looked into what are text representations. Why do we require text representations? It is very simple. That text, if it is given in the form of normal text that we speak, it is impossible for the machine or the model to understand. So it needs to be changed into some numerical form in the form of vectors, which can be given to neural network, and then processing can be done, and we can expect some output from there. Now, there are various kinds of text representations, discrete and distributed text representations. We have spoken about discrete text representations today. In that one, we have looked into one hot encoding, bag of words, and the term frequency, inverse document frequency. So these are basically discrete text representations where we get vectors from each of them, and these vectors are fed into the neural network and for predicting some output. Okay, and there is another text representation, discrete text representation, which is n-grams, that we will cover in my next session. And in my next session, I will continue with the distributed text representations. So with this one, I conclude today's session. I hope you all have understood why text preprocessing and text representations are important in NLP tasks. And in the next lecture, you will look more into various kinds of distributed text representations. And till we meet for the next time, keep learning, happy learning, and thank you all.